Hi guys, in this video I'm going to talk about generalized estimating equations, or also known as GEE. The material in this video comes also from the book Generalized Estimating Equations 2nd edition by Harding and Hilbert, and also the book Foundations of Linear and Generalized Linear Models by Ellen Agresti, and also from the famous paper Longitudinal Data Analysis Using Generalized Linear Models by Liang and Ziegler. And yeah, I'll put the link for everything in the description of the video. Okay, so what are GEEs? Well, they are extension of GLMs to grouped, which means also correlated data. These two fellows, Liang and Ziegler, they are the one who came up with this method in their paper from 1986, Longitudinal Data Analysis Using Generalized Linear Models. And so what is the difference between GEE to what we've learned so far? So again, in the linear model, we have the three assumptions that the y's are independent and identically distributed, that they come from a normal distribution, and that the mean is some linear function of the covariance, the x's. In generalized linear models, we keep the IID, but we generalize that y can have any distribution from the exponential family, and that the link between the mu and the linear predictor could be some function. So there can be some function of mu which is linear with the covariance. In GEE, we basically say that the assumption that the observation are identical is not valid anymore. So they come from, the observation are in groups. In those groups, we expect to have some correlation between the observations. So they are not IID. This assumption is no longer valid. Also, the way the GE works is very similar to the quasi-likelihood that in the previous video. So we don't specify the distribution of y. All we do is specify some mean variance structure, some dispersion parameter. And now, and this is the addition of GE, is that we also add a correlation structure of the correlation within groups. Okay, so again, this is a quasi-likelihood approach. We don't start with a probability model. We take the likelihood equations and modify them to add this correlation. And again, there might not be a valid joint probability. It might not even exist. Okay, so some nomenclature. It has a lot of names, yeah, these groups. So if the observation within groups come from different experimental units, then usually this kind of data will be called panel data or cluster data. If the observations come from the same experimental unit measured over time, then this is called longitudinal data. There are also other names. Okay, so I will just use the word group, which I think is the most general. Another distinction is that G is called in Harding and Hilbert's book population average G. And this is the original introduction of G in the Liang and Ziegler paper. And they also admit in the book that this is what most researchers think when they hear G. In their book, GLM, which stands for Generalized Linear Mixed Models, is called subject-specific G. In this video, I won't cover GLM, but in the next video, I hope to cover it, and also some of the differences between G and GLM. Okay, so why would we even think that there's correlation in the data? So for example, we could be looking at patient data, and the patient data doesn't come to us just randomly. It comes from, let's say, medical centers or hospitals. And we can assume that the data is correlated within each group of medical center or hospital. So for example, if we are looking at some disease which might be genetic, we could maybe think that in a certain area there will be some correlation in the data as opposed to data that comes from different centers. Okay, so this is one example. Another example is that maybe we are measuring a specific patient, but over time. So we have several measurements of that patient over time. So we can expect that the measurement of that patient will be correlated between each other inside each group. And in this case, the group is the patient. Okay, So these are two examples. What happens if we ignore the correlation? What do we say? I don't care about it. Let's just use regular GLMs. So the estimators are still consistent. So the estimators that we will get as the number of observations increase, they will still go to beta. But the standard errors are not reliable anymore. They are called naive standard errors. And in the Agresti's book, he gives a simple example. So suppose we have a 2x2 design matrix where we have time and treatment. So we have patients, and each patient we measure in 2 time periods, before maybe the treatment and after the treatment. And we have 2 types of treatments. We have A and B. Okay, and so we can assume some constant correlation. So we can assume that for each patient, there is some correlation between when we measure him in the first time step and when we measure him after the time step. Okay, and we also assume that there is no correlation between different patients. So if I measure one patient, it doesn't matter at which time. And if I measure another patient, it doesn't matter if it's in the first group or the other group. We don't expect any correlation between their measurements, because here we are sampling them independently from the population. So why can we assume this assumptions? Well, just for an example, if you think of the treatment as, let's say, diet, so we have 2 types of diets, and why the observed response is weight, then okay, if the diet works, maybe your weight goes from 100 to 90 kilos, or from 70 to 68. So there is correlation between how much you were and how much you will be before and after, but we don't expect so much correlation between different people. So let's say our model is some function, some linear function, some intercept plus the treatment and the time. And you can code the treatment as 0 and 1, and the time also as 0 and 1. Okay, so the treatment in this case is the between group effect, because our groups are patients, the different patients. And the time is within group effect, because for each patient, for each group that we have, we are measuring before and after. Okay, so it can be shown that the estimators for beta 1 and beta 2 are these things over here. The way you can see it is just maybe code the design matrix, as I said, with 1s for the intercept, the 0s and 1 for the treatment, and 0 and 1 for the time, and then solve a regular linear regression, and you will see that you get these things. And also you can get that the variances of these 2 coefficients are these things over here. And the way you do this is you just take these, you expand them, and you notice that you take into account the covariance, that here it should be 0 between these things, and here it should be rho. And if you do this, you will get these results. Okay, so we can see that we assumed some constant correlation, and we get that the variance depends on this correlation. Now, if we ignore this correlation, if we assume that the correlation is 0, so what we are basically doing, we are underestimating the between group standard deviation, and we are overestimating the within group standard deviation. So this small example, simple example, illustrates that if we ignore the correlation, then our standard errors are not reliable. Okay, so what is G? We start with the same likelihood analysis, and let me introduce some notation. So psi of beta will be the sum of the individual psi i's, which are the score vectors for the ith observation. Okay, and the score is again just the derivative of the log likelihood with respect to the coefficients, to the parameters we want to estimate. Okay, so we already saw in the likelihood analysis that this is equal to this thing over here. And now let's just break it down to first sum over the groups and then sum over the individual in each group. Okay, so this is just breaking the sums into 2 different sums. And then we can write it in matrix form like this. And of course, we know this is equal to this thing over here because this was the likelihood equations that we are working with all along. So in the normal case, we have that the V is a diagonal matrix, okay? But if we assume groups, if we assume clusters, then V here doesn't have to be any more diagonal. It can incorporate into it also some correlation structure. And in that case, then this V over here will become a block diagonal matrix, okay? So it will be V1, which is the first diagonal, and then V2, and et cetera, until Vk. Okay, and what we can do now is break down the Vk to the original Vks that we have. The Vk stand for the mean variance relationship, and these are still diagonals. So they can be basically taken to be the square root of themselves, yeah, to the power of half. And then incorporate here some correlation structure, okay? So for here, the V dash stands for mean variance structure, and the R alpha is a within group correlation structure. And I write here the underbar because alpha can be a vector of correlation structure, yeah? So for independent data, R of alpha is just the identity matrix, okay? We are treating each observation as independent. But G simply replaces the identity matrix with a more general correlation matrix. So again, if it's independence, R of alpha is I, we get that V of k is V dash of k, we do the analysis and we get back the same analysis as we've always done. So nothing new here. Okay, but we can also specify other correlation structure. For example, what is called exchangeable correlation or equal correlation or compound symmetry, which means that we have ones in the diagonal and the same correlation between every other measure in our group. Okay, and this could maybe be plausible when we are talking, for example, on the medical centers example. Another possibility is autoregressive correlation. And here we have autoregressive with degree of 1. So here the correlation between every two measurements will be alpha to the power of the difference in those measurements. So we have a matrix of 1 in the diagonal, and then alpha and alpha squared, etc. And this could be plausible when we are talking about repeated measures of the same individual. So maybe the measure that I take today is very correlated with the measures I took last week, but as time passes on, the correlation diminishes. We can also give an unstructured correlation matrix where we just say, just estimate each of those. We don't know what they are. We can give some fixed correlation matrix. And by fixed, I mean, we just decided this is the correlation structure and we give it. And there are other correlation structures, which are M-dependent, stationary, AR, non-stationary, etc. Okay, so how do we continue from here? How do we estimate the betas and how do we do inference over the betas? So now in the likelihood equations, we have an extra term. We have this correlation matrix, which we on purpose added to count for the correlation for what we believe might be the correlation in our data. If we knew the correlation matrix, like in the case of fixed, let's say I know the correlation and I just give it to you, then there is no problem. We just plug in that correlation matrix in the equation, and just like before, we get a system of equations, not linear. We use numerical methods and we get the betas. If we know the betas, we can also estimate the correlations. And the way we do this is using Pearson residuals. So the Pearson residual is the y minus the mean, or divided by the square root of the variance mean relation. Okay, this is the generalized Pearson residual. And how do we estimate it? So we can calculate Pearson residuals for all of our data. Given that we have the betas. Why do we need the betas? Because, well, how do we know the mean of an observation? The mean depends on the betas, right? It depends on the beta, it depends on the link function, etc. And the same goes for here. So we need the betas to calculate the Pearson residuals. Once we have the Pearson residuals, we can approximate the alphas. So for example, in the unstructured form, we just take the average of the correlations over the k groups that we have. Yeah, so we calculate the correlation of each 2 observations within group, and we take the average of it across all the k groups. For the exchangeable, for example, we take the average of all the upper or lower off-diagonal components of our correlation matrix, and we divide it by the number of correlations that we took. So because here we take the off-diagonal, there is half n minus 1, and here we are taking, for simplicity, we are assuming equal size clusters, equal size groups. Yeah, so nk is equal to some constant n. Okay, and then this is how much we are doing here, but we are also summing this up per every group. So in the end, we also need to account for this. For autoregressive, we can take the average of 2 adjacent points, right? So we just take the average between the first and second observation, the correlation between that, and the correlation between the second and the third, and the correlation between the third and the fourth. Each of those should be the same correlation, right? For AR1, we should expect the same alpha. If we assume it's the same alpha, they should be the same. So we are taking the average of them. And sometimes, again, like we see in many cases in regression, we also adjust for the number of parameters. And this is why you see the minus p in gray here. Okay, the problem is that we don't know either. We don't have the betas and we don't have the alphas. Okay, we don't have these correlation parameters that we added to the models. So we need to estimate both. And what we will use is an iterative approach. So we start with some starting value for the betas. For example, it could be the betas that we would get from regular GLMs. And then we estimate the alphas. Okay. And for this, we first have to estimate the Pearson residuals. And also we have to estimate the dispersion parameter. And the dispersion parameter we estimate, like I mentioned already a few times before, using the generalized Pearson statistic divided by the degrees of freedom. Okay, and now when we have the alphas, we can use them to estimate the new betas. And we do this again and again until the betas don't change. Or also another possibility is that the deviance difference doesn't change in our model. Okay, so this is the algorithm, the G algorithm. And then it can be shown that the betas that we get are consistent to the real betas as k goes to infinity. And here it's the case, yeah? It's the number of groups. Okay, what about the variance? So we managed to estimate the betas, that's all good, but what about how much we are sure about their significance? So notice again that just like in quasi-models, we hypothesize some covariance structure. Okay, we hypothesize some covariance structure. This is covariance matrix that we are putting in the likelihood equations. And it could be right and everything is okay, but again, we might be wrong. So the solution is to do the same as we did in the quasi models, which is to use the robust sandwich estimators. So I won't go over what we did in the quasi video, you can check it out, but just in short, we are using this Taylor expanding, and then we are looking at the variance of the betas, and we got that it's equal to the Fisher information matrix -1 times the variance of the score function times the Fisher information matrix to the power of -1, the inverse information matrix. And I stands for the observed Fisher information matrix here. Notice that in this case, the Fisher information matrix will again be different. It won't be the same as in the regular GLMs. And why is that? Because we are again using the variance, and the variance has its own, we are now saying it has its own group structure. So the variance matrix will be a block diagonal matrix, and we can also write this as a sum of group variance matrices, which will not be diagonal, they will just be symmetric according to the correlation structure that we specify. And if you want to look at the original paper, just note that what I call xk dk, they just call dk. Okay, so instead of this in their equation, you will see this. Okay, so this is about this is the change to the information matrix. what about the variance of the score function? Well, the variance of the score function is equal to the covariance of the sum of the individual scores with themselves. And this is equal to the sum of over all y and the sum over all j of the covariance of the individual score functions. This is the individual score function, right? So this is a vector. These are constants, some constants, and this is the random variable, yi. So if we replace all of this white thingies with a constant ai, this expands to this. And then if we look at the covariance, then this is a constant. It doesn't matter. It just goes out of the covariance. And what we are left with is that the constants go out. We get the covariance of yi and yj, and the vectors become dot product with themselves. We get this matrix here. Okay, if we assume independent observations, then the cross terms are 0, right? In this thing over here, it won't be a double sum. All the cross terms will be 0, and we'll just get a sum of the diagonal, you could call it, yeah, of the same index, I and I, which will be equal to this thing over here. And you can look that this is actually can be written in this form, like this, which is this form, which is exactly the derivation that we had in the quasi-likelihood, right? So we got to this derivation, and again, we have to decide, well, if we believe that our assumptions are correct, we just use the regular Fisher, then some things will cancel and we'll get the same regular variance that we had in the regular GLM. But instead, we can say, okay, maybe we are wrong, use the empirical variance, and then get a robust variance estimator, which is also consistent to the real variance. But what happens in group data? So this was for independent data. What happens in group data? In group data, we expect a correlation within group, but independence between groups, right? So we can write this sum over here as a sum over the groups first, and then the sum of all the covariance of each individual score with the others. And this can be written as a matrix form as this thing over here. Only vyk now is not diagonal anymore. In this case, the vyk will be full. It will be depending on the correlation structure that we specified. And again, we can write this whole thing as this matrix multiplication over here. And this time, via y is a block diagonal matrix. And just like before, we can plug in the model variance. Everything will cancel and we will get the same regular variance as before. Or we can use the empirical variance. And what is the empirical variance? Well, the empirical variance of yk, in this case, is yk minus the mean times yk minus the mean. Okay, it's the entire covariance matrix of y. And it can be shown that using this robust estimator, then the variance will go to the true variance of the betas as k goes to infinity. Okay, so this was all the theoretical part. In code, how you do this, there's a few libraries. For example, there's the GE library, and the code is GE, you give the equation, you have to specify the ID. ID is for the group or for the cluster. There has to be a variable that gives the same code to each member of the group. And again, you specify a family and a correlation structure. So the correlation structure can be exchangeable, it can be independence, it can be ARM, and then you also have to specify the M. For AR1, you specify 1. And this is the output you could get. You get the estimators, you get the naive standard errors and the naive z values, and you get the robust standard errors and the robust z values, and also you get an estimation for the scale parameter. Now, with G, I couldn't use weights. So there's also a package GPack, and the code is GLM. And here it's the same syntax as before, but you can also use weights. I'm not sure if maybe there is a possibility to use weights in the regular G, but I couldn't find it. Okay, so that's all I wanted to say in this video. In the next one, I will probably talk about GLMM and maybe compare GLMM and G. Hope you enjoyed and see you in the next video.